Okay, I'd like to introduce the concept of gravitational velocity. Gravitational velocity has helped me connect special relativity and general relativity into a single concept that I just call relativity, even though both of them use different equations for a lot of operations, including calculating time dilation, which is what I show here. So what is gravitational velocity? Well, gravitational velocity comes from the recognition that time dilation in a gravitational field is calculated by the escape velocity of the particular location of interest, which is typically the surface of a planet, but it could also be the orbit. The escape velocity is just the velocity needed to get out of the gravitational well of that planet or massive object. And what's interesting is that it's equal to the free fall velocity. You can see here a particle out in space starts falling, and then as it slowly gathers speed and arrives at the surface, it accumulates a speed, velocity free fall. And that free fall velocity equals the escape velocity, which is just a simple conservation of energy principle. Now, you can see that someone at the surface of the Earth experiencing time dilation that's calculated based on the escape velocity is effectively having space pass over them at the free fall velocity. And it's as though there would be particles or quanta of space-time that are falling into the Earth and accumulating a speed that is equal to the free fall velocity. So it's as though space-time is passing over the point or location at the surface of the planet and dilating time accordingly. This is exactly the same as if an object was moving through space at the free fall velocity and experiencing time dilation as calculated by just a standard Lorentz transform. So you see a connection between the principles of special relativity and general relativity. Now, this is more than just an interesting observation. It can actually be used to perform mathematical calculations with significance in physics. For example, let's calculate the time dilation for a GPS satellite. Well, the normal way to calculate this is to first calculate the gravitational time dilation, then calculate the velocity time dilation, and then multiply the two to get a total time dilation. The alternative way using gravitational velocity is simply to calculate the gravitational velocity of the satellite, which is the VG, and then geometrically sum it with the orbital velocity to get a net vector, V sum, and then just apply that net velocity to the standard Lorentz transform of special relativity. This will give you the same number. So here's the more detailed example of how to calculate it using the principles I just described. The velocity of the orbit is 3750 meters per second. Gravity, the gravitational velocity is simply the escape velocity, which in this case is 5400 meters per second. The net is the square root of the sum of the squares, which turns out to be 6,710 meters per second. You plug that into Lorentz, and you get a particular time dilation. And then you can compare it with the time dilation of the Earth using the escape velocity at the surface of the Earth. And you can see that the clock is traveling faster in the satellite. Just a couple more comparison points. This would be how you calculate it the old way. And they are the same. And I would argue that one's certainly easier to calculate, but conceptually it's much more simple. The takeaway is the time dilation is caused by space-time velocity. Either the velocity of an object as it travels through space-time, which is the classic special relativity case, or the velocity of space-time as it travels over an object, which is the general relativity case. Space-time curvature is essentially space-time velocity. Actually, it's the derivative, but close enough. And gravity, okay, is the gradient of gravitational velocity, or more particularly the gradient of time dilation, which is the true cause of gravity. Now, some will say this is just curvature or another name for gravitational potential, but these terms obscure rather than enlighten. And I ask you, how are you going to say that someone traveling in a straight line vector through space has gravitational potential? Or that someone traveling in a straight line through space-time is curving space-time? Using the term velocity for both cases is not only accurate from a units standpoint, it conveys the common principles that are being applied in both cases, and therefore the commonality between special relativity and general relativity. I hope you'll consider using this idea further and exploring it, because I think it will uncover lots of things that otherwise are very difficult to comprehend when looking at special relativity and general relativity. Thanks.